The formula for air pressure as a function of altitude is something like P of y is equal to P naught times e to the minus k y, which is derivable using the ideal gas law. But what is the pressure as a function of depth for an incompressible fluid with a pressure P naught at its surface? So this function, it turns out, involves a differential equation to get to. And the reason why is because air has a variable density, and that's something that can be related to the ideal gas law. So as the pressure decreases as you go to higher altitude, the air becomes more rarefied and less dense. So that makes it a little bit more complicated to get to something like this. But what we're being asked to do is to find an expression for the pressure as a function of depth for an incompressible fluid, which means that its density is going to be constant. So actually, really what this is asking us to do is to derive the pressure as a function of depth expression or formula that we started with on the key concepts slide. And maybe to make this comparable to what this says, I mean, that's in function notation P of y, where y is altitude. This could be P of h, where h is depth. But maybe I don't really need that, so maybe I can just go ahead and get rid of that and we'll pretend it doesn't exist, because we're really just wanting to analyze the physics that's going to give us this. So the way I'm going to do this is in analogy to the example we just looked at where there was an air column, but instead I'm going to look at a column of fluid. So if this is a pool of fluid, could be water, could be like liquid mercury in some kind of container, and my system is going to be a column that goes down to some depth. So there is that column. Now there's a pressure P naught here. I think I'd like to associate an area A with the cross-sectional area of this column, and the height of this column is really equal to the depth that we're analyzing for. So the free body diagram for this, there would definitely be a weight force, and maybe I can just write for right now that that is going to be equal to mg as a magnitude. It turns out, though, that since I said there is a P naught pressure up here, that means that there is going to be a pressure force pushing downward on this upper surface. And so let me throw in another pressure force here. I'm just going to throw a little bit to the side over here. So here's that other pressure force, and that is really going to be equal to that P naught multiplied by the cross-sectional area A, because I'm assuming that if the bottom has a cross-sectional area A, then that is constant throughout. In other words, I could also label as that area A being the top of my system. And then the force that really balances against these two is the upward pressure force corresponding to the pressure here at the bottom. And that force would have a magnitude of the pressure there, P, multiplied by A. So force balance, one way to maybe look at this is I could say if F net is equal to 0, then the upward force minus the two downward forces should be equal to 0. That's kind of the more formal way we've usually done things. I probably could have just said this is equal to that. In other words, pressure times area is equal to the sum of P naught A, which is, again, that sort of air pressure outside or whatever gas this is located in case it's not on Earth, plus mg. The way I'm going to analyze this further is to say the mass of this air column is going to be density times volume, and then the g will still be there. But volume is really, in this case, let me go and just erase that so I don't have to write the whole next line. The volume of this column is really cross-sectional area times height. So there it is, area times height. And so if I bring back the left side of this equation, I have a common factor of that cross-sectional area, so I can cross that out, and then I get the result that I was after. which was the formula for pressure as a function of depth in a fluid that we started out with. So we can see that that is also the answer listed on the slide. Although, actually, I guess maybe what I should have done here, I didn't write it in the same order, right? So let me fix that real quick. Or you can stop this video if you want. But, oops. Uh-oh. All right, maybe you've already stopped this, but I'm just going to rewrite it to make it match GH. Okay, there it is, and that's a wrap.